Right, we're carrying on with this thing. So what you've got is, remember what we said about ores, bores, corks, and mash. Right, what does that mean? If you react an alkali and an acid, you get water and salt. If you react a base and an acid, you get water and salt. If you react a carbonate and an acid, this is how you write carbonate. That was a bit slack. You get water, carbon dioxide, and you get a salt. And if you add a metal, if you react a metal with an acid, you get salt and hydrogen. What did we say? You're going to observe effervescence, another word for bubbles or fizzing. That's one observation. What was the other observation that we always come across? The solid will get smaller, or the solid will disappear. Okay, now the third one I said to you that I saw was the flask becomes warm or hot. I don't know if that's when this observation, I always related it to visual. What will you see? Okay, so that's the starting point. Yeah, so remember this is the MASH one: metal, acid, salt, hydrogen. That is a typo. It's supposed to be an arrow, the line that way. So you've got zinc reacting with sulfuric acid. So we're going to end up with zinc sulfate with the hydrogens being replaced. You're going to end up with zinc sulfate. So we're expecting zinc sulfate. The student could have used other metals which could be safely used. Right. I don't know how you've remembered the list of reactivity, right? So this is the most reactive and this is going to be the least reactive. So I learn it as when you get your results back at the end of a mock exam, the teacher will say, please stop losing careless marks always. And then I always think of chicken. Leave a gap. These are non-metals. These are reference points. Yeah. And then I put zoo is, and then if you look on your periodic table, you've got copper, silver, and gold on your periodic table. That's listed. These are like your jewelry metals or whatever you want to call them, right? Please stop losing careless marks always. So that is going to be potassium, sodium, lithium, calcium, magnesium, aluminium. That's carbon as a reference point. This is hydrogen as a reference point. This is zinc and iron. This is copper, silver, and gold. Right. So they've used zinc. Right, they've used a zinc. Let me get this highlighter. They have used zinc. Right, we could potentially safely use iron and magnesium. That's way too dangerous. That's 2-1 reactive. To make hydrogen, yep, that's 2-1 reactive. And copper doesn't react much, so that's no good. So it would be iron and then magnesium, which is just iron and magnesium. That's what they've given us. They didn't give us the choice of aluminium. Right, okay. Right. Okay, so describe a test to show that the gas is hydrogen. So what you do is you use a burning or lit splint and it gives off a squeaky pop sound. Right, this here again is, so we're reacting hydrogen with oxygen. So you've got two hydrogens, one oxygen, two oxygens. So we need to put 2 here. So now we've got 2 oxygens, but we've got 2 times 2, which is 4 hydrogens. So we need a 2 there. Let me get rid of that. There you go. Right, again, when I was, this has got a little typo in. So you've got cobalt chloride with water of hydration, cobalt chloride with water of hydration. In this reaction, there is a color change from blue to pink. Which word describes both cobalt? They are hydrated. Anhydrous. Okay, hydrated. I use the word hydrous. So I think hydrated would be a better word to use. That makes sense. Anhydrous means no water. Aqueous means it's in water, liquid. Saturated means it's got a single carbon to carbon bond. I think that's what it'd be applied for. Right, when the product in equation 1 is gently heated, another reaction occurs. Right, okay. I don't know if that's the right symbol then. I don't know what the original symbol was. I'm assuming, right, so reaction 1 and reaction 2, they're telling you that the reaction is reversible. Reversible. Now, I'm not sure whether that was originally like that then. I don't know. I won't be able to figure that one out without looking at it. But anyway, it goes from here, you add water, it goes that way, and when you go back, it goes from here back to the original and releases 4 waters. Right. A group of students, right, let me just get this out of the way. So a group of students investigated the reaction between marble chips, which is calcium carbonate, and dilute HCl, hydrochloric acid. They wanted to find the effect of changing the concentration of the acid on the rate of reaction. Right, teacher told them to do the experiments using different concentrations by diluting 100%, by timing how long it took, and at the same room temperature. Right, so you've got your acid here. These bubbles are the CO2 that's being produced. So it's calcium carbonate, so it's going to be the corks. It's going to be the corks. This is your carbon dioxide. That is your salt being produced, and that is your water. This is your carbonate, because they use carbonate, marble chips here, calcium carbonate, and that is the acid being used. Okay, so it's the corks acronym that we're interested in. The student tried to keep the amount of calcium carbonate constant by using the same number of marble chips. State two of the properties that should be right. Right, not only the same number, but the same overall mass and the same surface area. Okay, so they will affect the overall reaction. Now let's keep moving on. Right, this is an interesting one. Right, so we need to find out, what did the teacher say? The teacher said something up here. Concentration, time. So we want the mass. We need to make sure we use the same mass. We need to keep an eye on the concentration and the concentration of acid, and we need to measure the time, and after it's done, we need to check the volume of gas produced. So the teacher is saying she can only use results from student 1. So let's try to figure this one out. 6 marble chips, 100% concentration, 100 centimeters cubed of gas in 40 seconds. 6 marble chips, concentration, 100 centimeter cubed. There's no time. Let's do the next one. No marble chips. 60%, 100%, 70%. So there's no number of chips. Concentration, 6 marble chips. Time, there's no volume. Let's have a look. No volume of gas. Right, finally, you've got 100 centimeter cubed, 135 seconds, 6. There's no concentration. Where are we? No concentration of acid. There you go. Right, 5.3. Right, we have to draw this. Should we draw this? Yes, we have to. We can't be lazy. So she repeated the experiment. Oh, sorry, the students repeated the experiment. So they've given us the 2 axes, and then we just need to right, at 20 it was, the rate of reaction was 1.5 there. At 40 it's 1.9. At 60, so look here, I'm looking at 60 and 2.9. 60s 2.9, 70s 3.3, so they're going up in 10s and 20s. So 70s 3.3, so this is where they're trying to be a bit clever. So 80 is 3.9 and 100 is 4.8. Did I get that right? 1.5, 1.9, 2.9. Okay, that went up. So right, the anomalous result is that's a tough one. The anomalous result is right. So have I got a straight line? Oh, okay, I've got a straight line. So let's have a look. Yeah. Oh my God, did I just do that? Yes, I did. Can I put it through there? Is it just snap into it? Yeah, it's not very good. There you go. Right. So that's your straight line. It's going through most, if not all, of the points, yeah? So that there would be the anomalous result. And they normally ask you, right, suggest 2 errors in the experiment that could have caused this anomalous result. So what they're saying is the rate of reaction is too high. So that means the timer yep, okay. So this is what they've got in the mark scheme. The one that I could think of is the timer was started late. Right, so that means you've got a shorter time for the same amount of gas, which gives it a higher rate. Right? You could have said that there were more marble chips than the specified number or mass. That could have given more surface area, yeah. You could have had air in the gas jar or the measuring cylinder. That could have then given a false reading because you would have stopped early thinking that it's reached 100. Okay, what if the concentration was higher than 20? So the concentration may have been higher, so given a higher rate of reaction. Okay, the room temperature. So the temperature of the acid could have been higher, and we know that affects rate of reaction. Higher room or starting temperature. Okay. What else is there? Use your graph to estimate the rate of reaction at 50. So what they want you to get a ruler. Something like this. Let me get this. Let me try that. You go to 50. 39, isn't it? No, it doesn't like that. So I'm not going to bother with that. Right, whoa. Right, okay. So at 50, you get a ruler. You draw a line to your line of best fit. And then you go across. And we've got about 2.4. Right, that's fine. Right, that's done. Excellent. Right, okay. Let's try to squeeze this one in. Right, where are we? Oh, right. This here is it's a tap funnel. I know it as a tap funnel. You just need to put some in. You don't need to measure it precisely. Right, so right, that is a conical flask, I know. Conical flask. This is a gas jet, and these bubbles will be, let us have a look, CO2 bubbles. How do I know CO2? Because you're doing that. So with that, we're doing a corks, aren't we? Right, I know it's boring and repeating, but it's important that you get this into your head, yeah? A carbonate plus acid gives water, carbon dioxide, and salt. Okay. When excess CO2 is bubbled through lime water. Right, okay, so this is an interesting one. You've got lime water, you bubble through carbon dioxide. Let me do that. You've got lime water, you bubble through carbon dioxide, you end up with a solid precipitate, though. Turns lime water milky. This is where it comes from. Calcium carbonate is a solid. Now, when you bubble through some more CO2 through the same solution, excess, you end up with calcium hydrogen carbonate. What's the idea behind that? Right, so the first thing, look here. Ooh, okay, better stop that. Right, okay. Quite good actually. It turns milky or cloudy, and then after that, the cloudiness disappears. The white cloudiness disappears. It vanishes. Okay. Right. Carbon dioxide is used to fight fire because it doesn't support combustion. Right, what property? Right, the one that I know CO2 is more dense than air. Right, so it forms like a blanket. It's more dense than air. So like, look, for example, hello, what's all this? Do I need help? Not really. You've got a fire. Banksy, eat your heart out. Don't think so, somehow. That's your fire. The reason it's burning away because you've got loads of oxygen. What CO2 does, it comes in because it's heavier than that, it forms a blanket over it. The oxygen can't get in and the fire dies. That's the thinking behind it. Anyway, carbon dioxide is slightly soluble in water. It's got a pH of 5.6, so it's going to be weakly, or yes, slightly weakly acidic. Right, we'll call it quits there for this one. Mole question. No, we're not going to bother with mole questions, so we don't need that. Is this mole question? Nope. Okay, we'll do this one. Yep. Okay, let's do this then. You've got zinc, hydrochloric acid, so it's going to be a mash, and metal. It's going to be a mash one, yeah. So it'll be metal plus acid gives salt plus hydrogen. What you're going to observe? You're going to observe. What are you going to observe actually? You can effervescence, which is bubbling or fizzing or bubbling, and the metal will get smaller, or just put disappears as it reacts with the metal. Right, you've got 12 grams of powder, excess hydrochloric acid, so that means all the zinc will react. all the zinc will react, meaning all the hydrogen will be released at a certain temperature. The volume is measured regular intervals. So this was our starting curve with the things up there. Have you noticed it's reached a peak of 40 because we've used 0.12 grams. Right, we're going to repeat this same zinc, so we're expecting the same hydrogen excess, so all of it's going to react, but a higher temperature, so we're expecting a quicker reaction. So a quicker reaction would mean a steeper curve. It reaches the reaction, produces 40 centimeter cubed of hydrogen gas, and then that's it. It's just chilling out because there's nothing to react. So it will be A. Now, how can we say that? So what can we say there? A, why is it A? It's because at higher temperature, the reaction is faster, right? So you have a steeper curve. The gradient is steeper. Okay, right, watch this. You've got the same temperature, all the zinc's going to react, but they've given you half the zinc, so we're expecting half the hydrogen. And that makes sense because if you look here, what color can we use? Maybe, let's just use that. Right, can you see here, there? Have you noticed it's half the gas because we have used, let me write this down, we've used 0.06 grams of zinc, so we're expecting half the hydrogen. So now the same, just watch this, it's exactly the same. So we're going to say curve C because it has half the amount of zinc being used, so only half the volume of hydrogen given off or expected. That's it, done. Excellent. Right, listen, now it's getting too much. We're going to stop this because it's nearly half an hour. We will carry on next time. Thank you.